papers, maybe even first 2 weeks of papers should be easier. But we'll see. But nobody, oh. Okay. Yeah, if something catches your eye, let me know, because again, it's first come, first served. And we've got some of them taken already, but several not taken, and I guess I'll put up a few more debugging papers. So this is a first round of papers. Everybody's going to present one of these. And then once we're done with these topics, we're looking at essentially testing, verification, and debugging stuff. We're going to look at some more debugging stuff. We're going to look at some concurrency stuff, and we're going to look at some security stuff, probably some distributed systems stuff, because we have a lot of people, so we can get through a lot of stuff. I guess we're going to look at 26 papers, right? I mean, if we've got, it looks like 13 people, we'll end up getting through 26 papers this semester, which is a lot. Okay. Yeah, I guess if something ends up catching your eye, send me an email. So today the plan is that we're going to finish off the LLVM stuff. Okay, yeah, it's close enough. Let's see if we have anybody who went the other room. See if we have 5 people in the other room. So yeah, let's go through and finish off the LLVM slides. We're just walking through how to build a project using LLVM. Fairly introductory. I might go a little bit faster through the examples since we went through a lot of the core material. You can look back through the slides on your own as you're actually playing with the source code. I guess maybe we should actually let the students know that they can come in. So we can move on to the static analysis portion, which is, I think, where things are going to start getting a little bit more interesting in terms of techniques that you can use to actually do program analysis. Okay. So where did we leave off? So we were talking about the structure of the LLVM IR and the structure of bit code and how you can start to manipulate it, right? And I just talked about how LLVM IR is strongly typed, which means that everything must be given a type. There's nothing implicit. It's not like Python. It's not like assembly. You have to explicitly say what the type of everything is. And this means that if you have things like pointers, arrays, and structs, well, you have to explicitly say, here's a struct, here are all the things inside of it. I want to access this particular field within the struct very, very carefully. It's just a bit more work than you might have to otherwise. This also means, though, because this is a very low-level system, that the way in which you access things like fields within a struct or elements of an array is a little bit wonky. It requires a little bit of work that you might not necessarily expect. So instead of saying that you want to access, for instance, you've got a point. It might have fields x and y, right? You don't say, I want to access x of this point. If x is the first element in this struct, then you say you want to access the 0th field of x, right? So you use these numerical indices based off of the structure of the struct, or use numerical indices based off the position inside an array. And this is all done using the same primitive. So inside the bitcode presentation, the disassembled bitcode that we saw before, this is called a get element pointer, or a GEP. And that's also the name, essentially, of the class that is used to represent this. Well, get element pointer is the name of the class that's used to represent this inside the LLVM API. So if we look over here at a simple little program with a struct, x and y, and we might have pointer to a bunch of these, and we try to access some element, the fifth element of this buffer pointed to by that pointer, and we access the Y field of that. Now we get to see how all this works. You use a single instruction to compute where this is in memory. And that's the get element pointer, and you can see that the first thing it takes in as an argument is the actual pointer that you're playing with, or whatever you're playing with, and then it takes the offset based on the fact that it's a pointer, and then the actual field, right? So you can again see, oh, this is the fifth element, pretty straightforward, and we're accessing the, in this case, 1th field, Y, right? Okay. Questions?
Why for this buffer 5, it's using I64, it's like very large. Right?
Yes, that's because I compiled it on a 64-bit machine.
Right, but then for the next it's using I32.
This is because there aren't a whole lot of fields in any given struct usually.
Right.
So you're probably not going to have 65,000, more than 65,000 fields in a struct.
Oh, okay. But you can have large arrays, right?
Yes, absolutely, absolutely. Make sense?
Yeah.
Excellent. Okay, yeah. So exactly the instruction there. Where else can you get information on this? There's an excellent programming manual online. You'll probably refer to this when you start to figure out how to play with API, the LLVM API. And there's also the LLVM language reference manual. So the LLVM language reference manual tells you things like, oh, ret is return. Get element pointer is the instruction that you use to actually compute an address of a pointer, right? So there are good resources online. There's also a big community, so if you have a question, there's a good chance someone else has asked the same question and you can find some resources online for it. If not, chances are I've actually asked that question of myself and found an answer for it. Also, the header files are there. I highly recommend looking at the header files. They're confusing. You get used to them. There is a structure to them. There's a methodology to them. It's painful, but it works. And there's a lot of documentation in there. So let's actually look at an example of how to create a static analysis. And the source code for this is available on my website. We'll look at a dynamic analysis after this, which is a separate issue. So an analysis is going to be organized into different sorts of passes. So if you're looking at an entire compilation unit, you'll use a module pass. If you only want to look at a function at a time, you'll use a function pass, etc. So what you're going to do, if you make an analysis, is declare your pass, register your pass with LLVM, and then define the actual pass using whatever code is relevant to do the analysis you want. Let's look at an example. And let's try to look at this problem of just counting the number of static direct calls to every function in a program. So let's see. Well, the underlying idea here is that, well, if foo is called 5 times directly inside your program, then you want to figure out, oh, the associated count is 5, right? If main calls printf twice, and it doesn't get called anywhere else, then you want to have the count 2 for printf, right? So, you declare your module pass. Pretty straightforward boilerplate here. Let's go through this very quickly. You'll declare a few standard functions here. You'll have a run on module function, which just says, this is what I want to do to the module. And it returns true if you change that module in some way. And we also see some standard boilerplate again. You have to construct whatever pass you're making, deriving it from the appropriate type of pass. So since we're looking at an entire module at a time, we derive from module pass. And you have to always have a static ID for your particular pass. And pass that into the constructor as well. Just boilerplate again. You just have to do this. Okay. And then you can register it, and this allows you to actually call your pass via the command line using opt. So this is, again, the opt tool that comes with LLVM. It's just a plug-in infrastructure. So we actually want to define what our pass does, then we need to go into that run on module function and start to make it do something, right? So for us, well, we can go through every function, and then go through every basic block inside every function, and then go through every instruction inside every basic block, and just say, we're going to do something on every instruction. So very compositional, right? We don't actually care about the rest of the structure. We just want to look at every instruction and kind of intuitively ask ourselves, is this a call? What does this call instruction make a call to? Increment the count for that, right? Okay. So, how does that end up working? Well, we can call getInstruction on a call site constructed from the instruction, right here. Magic C++ conversion happens right here. Converts an instruction into a call site structure. This is just the magic incantation that LLVM uses to say, is this a call or not? Again, I can't really change that fact. That's just what you do. This down here is how you figure out what was called. And I mentioned before that call sites could cast particular functions, right? So this is the same magic incantation we saw before. We're casting something to a function and then figuring out whether it's a direct call or not. So does anybody remember why we have to say if not fun, return? We talked about that last time. Why might fun be null?
Because it may be confirmation.
Yeah, exactly. So if this particular call site makes a call to a function pointer, then the called value will be a pointer instead of a function. Okay, so we try to cast this to a function, and if this cast type, and well, really, the actual type of the function could be something else. You know, maybe a function can take as an argument a pointer to a particular type of struct. Now, the way polymorphism is often implemented, it might actually be a function to a pointer of a different type of struct, as long as they're compatible, you know, as long as there's appropriate subtyping or something like that.
So a function, you want to say that a function might have same name, but it is polymorph?
Well, it could be that there's a compatible function that isn't exactly the same type. So, you know, maybe there's a function that you've got a point class with 2 integers and a point class with 3 integers.
Okay.
Well, a point class with 3 integers is a subtype. It's a type of point class with 2 integers. It's just got something extra, right? So you could, in theory, cast a function that takes an argument of this super type with just 2 integers.
Okay.
So just because of that messiness in terms of the details, you're dealing with a lower level system. You have to do all that manually. So there could be casts involved. The bottom line for that really is just, that's kind of magic boilerplate. For now, it's just magic boilerplate. Otherwise, you might not get the results you want. Anything else? Okay, let's move on. So then you have a nice little print function here that can print out your analysis results. We've collected all of our results in the map, right? Yes, inside our counts map. And so we can just iterate through all of the elements of this counts map and print out the function name and the actual count, right? So pretty straightforward stuff. You can download the code, you can run it yourself, hopefully. You should be able to run it, compile it and run it yourself. I recommend trying that. That's a good first step. Make sure that these things work.
So one question.
Yes.
From the previous question, you said that if a function like it is a superset of something, a superset can be cast into a smaller thing. But what if like it's a function, it has 2 ints, and the same name function has like 2 characters? So
that would not be compatible. So it's not necessarily
How do you-
superset. It's what you call a subtyping relationship. So when you look at inheritance in Java, right? You know, you could say, well, there's a point 3D, which is a subtype of a point 2D, because well, a point 3D has 2 points. You know, it has an x and a y.
yeah.
So it's still a point 2D. You just got a z as well. So if you have some function that can take a point 2D, well, then it'll take a point 3D.
So my question here is, how do you separate them out in the code? Like, how do you want to call that particular function?
If you know that you want to call one directly, just use that function. just use that function directly. So it's only when you don't necessarily know which function you want to call that this sort of thing starts to come into play. Or there's some other indirection that's going on there, usually, that makes these things messy. Okay? It's all about self-typing. Okay. So now let's look at creating a dynamic analysis. We've looked at the static direct calls, and that's a static analysis. We're not looking at the running behavior of a program. In contrast, we can look at the dynamic calls inside a program instead. This means looking at what calls actually executed inside the program and just counting them as they happen, right? Okay, so how would we do this? We can't do it by just running the original program, right? Because the original program, if you compile it and run it, it'll just run and you won't get any results. So you have to somehow change the original program to gather the facts that you want for you. So that's what we're going to look at here. The underlying idea here is now we're still going to use these module passes, or these different passes for analyses, but we're going to use them to modify the underlying program. And then you compile this modified program with additional instructions that will gather the facts that you want. And then you can run this new version of the program on whatever inputs are of interest to you. So we're not going to go through this code in detail. It's going to be very high level, just to give you a big picture of things. That's because it's a lot more complex. But I recommend going and playing around with it and maybe looking at it.
In what sense do you mean modify?
I mean, we've got one program, right? This original program. In order to determine something like how many times every function is called, we're going to have to insert new instructions into it.
Maybe some flags or some count?
Exactly. Exactly. So intuitively, you might say you want to maintain a count for every function that gets called. So you'll need some sort of map inside the actual program. You'll need to insert a map into the program that says, okay, for every function as it gets called, I'll increase the count. And then you can print out this map when the program terminates. Or record it to a file, or whatever. Okay. Yeah, so let's say that we have some function foo that calls some function bar. Suggestions. Tell me at a high level, not in terms of the LLVM code, but at a high level how we want to actually go about implementing this sort of an analysis.
You execute foo, and then inside that you find bar and you increase the count.
Okay, so one of the ways that we can do this is that we can insert some instructions into foo so that when we look at foo and we see that it calls bar, we can increase the count for bar.
Or we can insert an instruction into bar and increase it by 2.
Okay, so I'll hold back on this increase by 2 for a moment. But there's an alternative approach you mentioned where we can wait until we get into bar, or analogously into foo, and increase the count for it there. So we have keep counter for each function. We have 2 choices. This is excellent. That's exactly what I wanted to find out. We can either increment the count for each function as it starts, right? We can increase the count for foo when we enter foo, or we can increase the count for bar when we see bar at a call site. Are there trade-offs? Are there reasons to do one or the other?
If you talk about atomicity and like threading, like the function might be called, but bar might not be called for some reason.
Okay.
There are other lines of code in there.
Atomicity increases, adds a whole extra level of complexity to this. Let's not worry about that, because even what I'm going to show you won't work in that scenario. Because even every increment alone, you'd have to have extra synchronization around, or some other atomicity requirements provided so that your increments are atomic.
So what if we have virtual functions, right? Like this foo is implemented in several different classes.
Okay.
Then if we do it the call side, it will be counted no matter, right, which, if we have function pointer, right?
Mm-hmm.
If we call function pointer, then if we do it the call side, we'll just call, okay, how many foo were called. But if we have, as it starts, we have to put in each implementation of this function foo, right?
Okay, so if you have function pointers, then things get a lot messier.
Right.
So I'm going to cheat and say that for now, let's consider static direct calls and not worry about function pointers. Because even what I'm going to show you isn't entirely precise for function pointers. It gets messier. There's a simpler problem that arises. Suppose that we have some function, foo, inside our code, and it calls printf. It calls printf directly. Where do we insert the instrumentation for printf?
So we can't go inside.
The call side.
Yeah, it has to be at the call site because we can't change printf. Printf is in some external library code. So you've got to insert that code for printf at the call site. But, maybe for these other things like foo, that's part of our code, it's easier just to add the instrumentation when you enter the function. So I'm only going to show you one of these, but you'll see in the example code that I've given you inside this demo on my webpage, where you can get this code again, you'll see both. Now, what's one of the trade-offs if you add that increment at function entry? Is there any reason why that isn't necessarily desirable? Maybe getting back to what you mentioned a moment ago?
In the sense that we have to put everywhere,
Well,
every single function.
that's okay because every single function is still probably less than every call site. Well, assuming everything gets called. Because you'll have multiple calls to even one function. But if we have one function that's called directly and indirectly through function pointers, we'll start counting the function pointer-based calls as well. So there's some inaccuracies. If we're saying I only want to count the direct calls, then it won't be entirely precise. Ignore that for now. Just a demonstration. But you have to bear these things in mind, right? There are these subtleties that come into play when you're building up these analyses. And you have to worry about these choices. So for now, let's just increment it at a function entry. Demo code has both again. We can use numeric IDs. This is usually a little bit simpler. So, okay, when we call bar is 2. So let's pretend this says 2 instead of, well, 1. Okay, so we're calling, at function entry, we're increasing the count for foo, so we increment 1. It's all right. Yes, excellent. Either too much coffee or not enough coffee. Okay. And usually this is actually a little bit easier if you do it by inserting function calls. Because if you do it this way, what do you have to play with? You have to play with indices. It's easy to get wrong. If you want to do something more complex than just increment one thing, then you've got a whole bunch of things to insert, and it gets messy. So it's easy just to insert a single function call to whatever you want, and have this be part of an extra library that you write inside C code. So that way you can write this normally, just like normal C code, and have it called by whatever you're doing. This is the approach taken by the demo code that is available to you. So go, play with it, have fun. Okay. So if we're looking at how to actually add external libraries somewhere. So what does this look like overall? Well, we've got our program that we want to analyze, and we compile this to bitcode and pass it into our analysis tool. An analysis tool is essentially the LLVM terminology for something that combines a bunch of passes. And in our case, that's an instrumentation pass, where we add our instructions, and a compilation pass, where we're actually going to compile this and link it. Okay. So then during the compilation process, we pull in our runtime library with those functions that implement the things that we called inside the instrumentation pass. And this gives us our modified program, and we run that on a single input to get our results. Now notice this means that our results are only for a single input. So we talked about this briefly before, I think. Static analysis is going to look at all possible behaviors, and dynamic analysis just looks at behavior for a single input. Okay, so bringing it all together, all of this passes, tools, etc., is organized into what LLVM calls a project. And the easiest way to start is by using the demo code I've given you. I'm also giving you templates for the project, but if you want to use the demo for, say, a term project as a basis or something along those lines, feel free. It's a lot easier than starting from scratch. I've gone through most of the suffering for you. Okay, yes. And in terms of just some extra tips, there's a lot of informative capability inside the API. If some type exists that you want to get the name of, just call getName. Or rather, if there's something inside LLVM, like a method or a variable or whatever, you can call getName on it. For types, you actually have to call type.dump. And then you can usually just print stuff out using an outs helper function inside LLVM. So, a static analysis is going to consider all the different possible behaviors of a program without running it. So that's the key benefit here. You don't need a concrete input to run this on. You'll consider everything. And you can look for properties like, do I ever dereference null pointers? Do I leak memory? Do I violate protocol specifications? Are files open when they shouldn't be? Or does my program terminate? Now maybe there's some red flags here, right? If I ask the question, does my program terminate? Is it guaranteed to always terminate? Does that bring to mind anything?
Infinite loops. Infinite loops.
Infinite loops, and on a theory level, how does that cause a problem?
Memory leak?
Oh, well, not necessarily a memory leak. What you could have, on a theoretical level, this results in things like,
Stack Overflow.
it results in undecidability. So it reduces to the halting problem. How many people have heard of the halting problem? Okay, not that many. Out of curiosity, how many people have taken a theory course? Even fewer. Okay, none is fewer. Okay, so essentially, if you'd taken a theory course, then you would have found out this is provably impossible. You cannot do this in general. You can do it some of the time, even a lot of the time, with appropriate limitations on what sort of programs you're looking at, or on the structure of certain programs. So it turns out that most of these problems end up being not so doable in theory. But if you make some allowances for wiggle room, if you allow your results to be approximate, then things can be done. Maybe you can say, well, for most programs, I'll determine whether or not they terminate. But then for some programs, I'll say, I don't think this terminates, and it actually does. So if you allow for some incorrect results some of the time, suddenly things become possible. And these are the pragmatic issues we have to deal with. So we have over-approximation and under-approximation that end up simplifying these technically impossible problems.
So by terminate, you mean that it terminates while running, or when it's run its course?
If it ever even stops, ever. So maybe a lot of programs you want them to stop.
Maybe if it's done its course and you've got the result and then it stops.
Right, right.
Is that considered terminated?
Yeah, absolutely. It's technically, so maybe a program has an infinite loop, or for a particular input, maybe a program will run forever, and it's technically impossible to prove in general that a program will terminate. It's a bit mind-boggling. It boils down to a paradox that
If you
arises.
want your program to terminate.
Well, I mean, unless it's a server program, probably, yeah. Okay, so when we look at these over-approximation and under-approximation issues, we have sound analyses that over-approximate properties of interest, is how we'll frame it. And you're guaranteed to find violations of these properties, but they may raise false alarms. Okay? So in other words, sometimes the property will hold, your program will be safe or something like that, and you'll say, I think there's a bug. Right? And it'll have complete analyses, which are under-approximate. And as a result, their reported violations are all real, but they may miss things. There's some trade-off here. striking the right balance between these is essentially one of the big struggles in making some sort of program analysis that is actually useful, right? Because either you're providing noise by raising false alarms, or you're missing actual bugs, in which case maybe people aren't going to trust your analysis. So you want to be as minimally approximate as possible. You want to be as close to the real results, to the right results, even though that's impossible. Okay, so if we look at how this fits into program behavior, we have the possible program behaviors, and over-approximation gives you this larger set of potential behaviors that you'll be looking at. You know, maybe some behavior isn't actually possible, but you think it is because of your over-approximation, and that's why you raise a false alarm. Under-approximation looks at a subset of possible program behaviors, and this is why you may miss some things. And if you just look at one execution, it may or may not overlap with your under-approximation. So one execution is actually a type of under-approximation. Okay, so let's just look at a simple example, and this is in the context of something that we call data flow analysis. This is one type of static analysis. And we'll talk about others, especially over the course of this semester. We'll end up seeing other static analyses too. So one reason why it might be useful to know if a number is ever negative, or whether it's, say, negative, 0, or positive, is that you could ask yourself, well, is this ever going to be an invalid offset in the memory? Or you might ask yourself, will I ever divide by 0? These are useful things to know, right? So we want to approximate the program's behavior. We're going to do this by looking at the concrete domain that the program actually works on, in this case, integers, right? And we're going to map it to an abstract domain that simplifies the problem into something more manageable. And in this case, it's going to be, well, a number could be negative, 0, or positive. And we also have these other two things we're throwing in there, and you'll see why a bit later on, which are top and bottom. And top basically means we throw our hands up and say, we don't really know. This is part of our approximation, right? The ability to say, I don't know. So that's why we're joining that in there. And then we also have bottom, which basically says, I haven't really considered this yet. To be determined. Okay. And we have this mapping from the concrete domain to the abstract domain. So, okay, 5 is positive, negative 3 is negative, 0 is 0. Pretty straightforward, right? And this is really, notice, combining partitions of the concrete domain. So you can see how some of this approximation is happening. Instead of this wide range of positive numbers, we're just looking at them all, lumping them together. Now we have to worry about transfer functions. A transfer function defines how the program behaves over this abstract domain. So if you have a positive number plus a positive number, you get a positive number. If you have a negative number plus a negative number, you get a negative number, right? Pretty reasonable. If you have 0 plus negative, you get negative. If you have positive plus negative, we don't know, right? And so this is where some of the approximation comes in. This is how you simplify things. So that's why we have top, and then, well, if you've got something divided by 0, technically it's undefined, and to be determined, they both fall into the bottom, that's okay. And we also need to have what we call a meet operator. So this is where we have to take into account that, question?
Yeah, so divide by 0 is the only case that comes in undefined, or
anything you haven't seen yet. And we'll see how that comes into play in a moment. We're going to look through an example of this. Okay. So we also have a meet operator, and this combines the results across program paths. So remember, we're doing static analysis, and this means that we have to consider all the possible program paths. But maybe in one execution, you could take one path. In another execution, you could take another path. And somehow you have to combine the results from those paths to say what's possible when they come together at the end. And that's the purpose of the meet operator. Okay. Ultimately, a lot of this can be pretty subtle. So this particular formulation isn't sound or complete. It's still useful, but it's not sound or complete. Can you think about why? Another way of framing that is, how does this behavior maybe not reflect actual behavior inside a computer program?
Strings or other vectors.
Let's even assume that our programs only play with integers. We can make the problem as simple as possible, and it's still not sound or
There could
complete.
be multiplication or division.
We can assume we've got multiplication and division defined in here too. That's okay. Even what I'm showing you.
I mean, if we have signed integers and you do plus and you do summation of positive integers, you can overflow
Sure,
and
absolutely.
get into the negative.
Absolutely. This is a very common issue. A lot of static analyses don't take overflow into account, because overflow means you have to consider, well, okay, we've technically got this modular behavior to worry about, and reasoning about modular behavior is more complex than just saying, add two positive numbers, get a positive number. So this is a common simplification. Yeah, absolutely. And as a result of exactly this issue, overflow, well, we're representing some behaviors that can't actually happen, and we're missing some behaviors that can, right? And so that's why we're neither sound nor complete. Now, when we look at some analysis like this, we have to worry about things like true positives, true negatives, and false negatives. So let's say our goal is to prove that a program never divides by 0. Well, let's frame it differently in order to make this simpler, actually. Let's say that my goal is to find division by 0 errors. What would a true positive be?
Divide by 0 actually happens.
Yeah. You say there's an error here, and there's actually an error. Absolutely. What's a false positive?
You say error, there is no error.
Yeah, you say error, there is no error. True negative.
You said
It's
no error,
definitely
there was
not
no
an
error.
Yeah, so you don't report anything, and there's no error. False negative,
You reported nothing, but there was something.
right, you report that there, you don't report anything, but no. We'll look at implementation in a moment. Let's look at an example here. So if we've got a simple program here, it's the same one we looked at last time, where you're just summing up the numbers 1 through, I guess, less than n. We can start off with sum being 0, that's reasonable, and I is positive, right? And we could go down to its successor, 3, and we say, well, sum is 0 still, and I is positive. Reasonable, right? Okay, so we can keep on going down to the end, because we have to go somewhere. We have to choose one of these branches to follow as we're reasoning about the program. So we go down to the end and we say, sum is 0 and I is positive. But sum is probably not going to be 0, right? If n is something, reasonably large, sum is not going to be 0. So what do we have to do? What didn't we do that we should have?
Take a branch.
Yeah, we still have to consider this branch. We never considered the behavior when you go through the loop. So we have to go back and consider the behavior through the loop. And so when we come down here, well, we say, okay, I equals I plus 1, 0 plus 1 is guaranteed to be positive under our abstraction, right? So sum is now positive, I is positive, life is good. But this has an impact on the behavior of the program. We already considered 3. We've already been there. We've already got results for it. But we have to go back. So what should the results be? This is where we're going to apply our meet operator. Yeah,
Top.
yeah, it's top. Why is it top?
Because it could be, it's varying, it's not like, it can be the 0 or positive.
Absolutely. It could be either 0 or positive, and we can't say for sure, because it'll depend on the input, or it'll depend on the value of n, right?
Theoretically, some could be negative as well. If you overflow, it'll go into negative.
This is true.
Yeah.
This is true. But we accept this limitation of the underlying analysis. That's a failing of our abstraction. There is a lot more work on doing analyses using bit vector representations that are a little bit more precise because you can capture that modularity, but you do pay for the precision. Okay, yeah, so it should be, yes, to represent the behavior across all executions, it should be top. So we have to propagate this new behavior here up to something that was changed by it, right? We had to revisit something because one of its incoming values changed. And we have to propagate that down to the end because we don't know what the sum could be at the end. Reasonable, right? So at the end, sum could be anything, but we have a clear picture at least. We know that I is positive, and we know that at various places sum is positive, right? So we end up continuing this until we reach a fixed point. So when we stopped down here, I could continue going back through, I could have continued, for instance, going back through this loop, right? But sum is going to stay positive based on our abstract domain, right? Based on the abstraction we're using. Sum is going to stay positive, I is going to stay positive. These aren't going to change anymore. So we've reached what's called a fixed point. No matter how many times we keep propagating things through, the results aren't going to change. So we continue on until we hit that. And one thing you should consider is that the efficiency of your analysis depends on the order in which you visit the nodes, right? So I started here, I came down to 3, I came down here. I could have taken the other branch.
So
Yeah.
when you say that nothing changes, you have to go through all the passes in order to be sure that nothing changes. Or is it that like for 2 or 3 passes nothing changes and then you say that it's not changing?
We're going to come back to that. This is a good question. This is a very good question. So the issue is essentially that you have to be a little bit careful about how you define your abstract domain. If you design it carefully, you can guarantee certain things about nothing changing. Good question, though. Okay. So essentially what you want to do is what we call a topological ordering. And one way of doing that is something called essentially reverse post order. So you want to visit this before any of its successors, because this is going to affect the behavior of its successors, right? So if you do that carefully, you can optimize essentially the efficiency of your algorithm. Okay. Will it always terminate? This gets back to your question. Will this one always terminate?
Yes.
We've looked at one program. Maybe it doesn't terminate for a different program.
For this, are you asking for this particular piece of code?
Well, we can ask for any code. For this code, I'll agree with you. I'll agree with you, because you said yes a moment ago. And I said yes a moment ago. So for this code, I'll agree that it's always going to terminate. Do I have,
This continue until we reach fixed point. Could it be that we never reach some fixed point?
If you're
Is
not
it
careful, you could never reach a fixed point. Yes, it depends on the abstraction that you use,
Right.
on how you transform the concrete domain into the abstract domain. Oh, there was something else? No? Okay. So we end up guaranteeing this just by being careful about our abstract domain and the transfer function that we use. And for basic analyses, you always want to use a monotone framework. There are some other theoretical complexities behind this that we're not going to dive into. They are relevant, but we can maybe touch them as they become relevant to the papers we look at. If you're more interested, then feel free to look into this on your own or ask me about them. We could do an entire course just on the structure of data flow analysis. And there are lots of subtleties here. We're not going to do that. But as things become necessary, we will touch on them. So we had our abstract domain as being -0, positive, along with top and bottom. And they define what we call a partial order. And in fact, they define what we call a lattice, which is where any 2 elements inside this partial order will have a greatest lower bound and a least upper bound, right? And you can see that in the structure here, right? So all of these things are ordered, right? This is less than anything in this row, which is less than top. in terms of how much we know about it, but these things aren't ordered related to each other. You know, negative is not greater than or less than 0 in terms of our abstraction, in terms of how we're using the structure of the program, even though negative numbers are less than 0. Okay? That slight ambiguity is clear? Good, good. Okay,
This
so
framework does not guarantee that the program will terminate.
this framework does.
So in the previous program, we reached, if n was, say, instead of I less than n, if we had I greater than n, okay,
Mhm.
and n was say 0 and you start from 1, then we still reach a fixed point because the positiveness, the sum will be positive always, I will always be positive. So we have reached a fixed point,
Yes.
but the program is not terminated.
The program won't terminate. That's okay. Our analysis will. Even if the program doesn't terminate, our analysis will. That's one of the benefits of static analysis. So the issue here is that abstract state can only move up the lattice at a statement, right? When we revisited a node, we went from, when we visited the first time, we went from bottom to one of these, right? And when we visited it a second time, if the results were inconsistent, then we found the greatest lower bound, least upper bound, sorry, and we went up to that, right? So we're bounded in terms of the number of times we actually visit a statement by the height of the lattice.
So each state by default is not defined.
You start out this way, right? And we'll see that in an algorithm in a moment. Okay? So this means that at most you're essentially going to visit every node the height of the lattice times. And that's why we terminate. We have this structure. Reasonable? Excellent. Okay. I guess I already explained that. I've spoiled the surprise. Oh well. Yeah, it's enough because we're only going to visit each node essentially the number of times that is the height of the lattice. Now technically, you can have lattices that are infinitely large and still guarantee termination. So things do get more complex. Things do get more subtle. We're not going to dive into that quite yet. Maybe we won't dive into that at all. But it's interesting stuff. Okay. So yes. I guess this is just a review of what I already said. We actually need to model the program state at every statement. We're using our ordering and something called a worklist algorithm. Anybody used a worklist algorithm before? Anybody heard of a worklist algorithm before? That's what I was expecting. Okay. I expect that in part because, I guess we're out of time. So we'll pick this up on Tuesday. Out of curiosity, does anybody have a class after this? No. So I debate modestly the potential of shortening our class on Tuesday by half an hour sometimes and increasing projector.
Oh, I was going to say the projector
Oh!
turns off.
Very clever. Okay. Yeah, devious. Okay, so we can't do that. We'll pick this up on Tuesday by going through an implementation, showing you how to use a worklist algorithm to actually compute this if you want to implement it. Devious.